Hello, my name is DJ Pantone, and I'm doing problem 2915, which says that a proton that has an initial velocity of 800,000 meters per second is brought to 0 meters per second by a new field. So, on this left-hand side, I started off by writing some basic values that we're going to need for the problem, such as the initial velocity of the proton, which was 800,000 meters per second, its final velocity, which was 0, the mass of a proton, and the charge of a proton. Now, we were given these on the first day of class, so I suggest you go back and look those up if you don't remember them. Anyways, I started off by drawing a picture, and in this picture, I just chose to do parallel plate conductors. It's not necessary, but it was the easiest way for me to visualize it. So, you have your proton here, and it has some initial velocity that's going this way. However, there's a force pushing back on it. So, the very first question was, what does the proton go from a higher potential area or a lower potential area? And the answer to that is the proton moves into a region of a higher potential because in order for it to actually lose speed and go from 800,000 to 0, that means it has to have something working against it. Otherwise, if it was going this way, it would definitely speed up and go faster towards the negative plates. Whereas this way, it slows it down, until it finally gets to that 0 meters per second. Anyways, this side, as we know, will have a higher voltage than this side, where this will be 0 and this will be some x that we don't have an actual value for. So, the next question was find the change in electric potential that causes the proton to stop. So I started with the basic equation for energy, which is E initial equals E final, and then I broke it down to its two components of K initial plus U initial equals K final plus U final, whereas kinetic energy and potential energy. So I wrote down the values and said that it was 1/2 the mass of the proton times the initial velocity of the proton plus the V initial times, where V is voltage, times the charge of the proton. But the thing is here that we have to remember that we're trying to find the change in velocity, not or change in volts, not the actual volts. And so here we say that change in U equals change in V times the Q of the test charge. And so we're going to come up here and pretend like the VI that is right here is going to be our 0 point, and this is going to be our final point. And so whatever is between this will be the change in voltage. So this voltage initial will act like 0 because it's our 0 point, because there's no change from that point. Anyways, we then come over and take the mass of the proton times its final velocity, and then the final voltage times the charge of the proton. If we plug that in, we get that you have 1/2 times the mass of the proton times its speed plus 0, because like we said up here, we're going to treat this like it's the 0 point because we're trying to find the change in voltage, not its necessary value. And then we come over to the other side and we have 0, since the final velocity of the proton is 0, plus voltage final, which will be our change, times 1.6 times 10 to the negative 19th, which is the charge of a proton. Anyways, if you take this number and divide it by the other side, what you get is 3340 volts, which will be your change in voltage.